All right, class, today I want to pick up where we left off yesterday on precipitation reactions and solubility product and solubility, molar solubility, all of those terms. So what we're going to do today is, one of the things that's interesting about precipitation reactions, we would like to be able to predict whether if we add two substances together, do we get a precipitate? And they could be dissimilar substances. So maybe I add lead 2 nitrate with sodium bromide, and I want to know, based on the concentrations of the lead 2 nitrate and based on the concentrations of the sodium bromide, if I add those together, do I get a large enough solubility product of the lead with the bromide for it to precipitate out? So that's what the focus is going to be for this lecture. It should be a short lecture compared to the other ones. And the other thing I really like about this lecture is, I hope that once we get through today's lecture, you will integrate chapters 15, 16, and 17 together. 15 was the tools chapter, and I said you must know these tools in order to be successful in 16 and 17. 16 was the acid and base chapter, and then 17, buffers in the front end, titration in the middle, precipitation at the end. But you'll see throughout all of these, they have connectivity in that we're looking at a balanced chemical equation, we're looking at the products, and we are either neutralizing an acid or neutralizing a base, and then maybe we have a salt left over, and that's the conjugate, has the conjugate base of a weak acid or the conjugate acid of a weak base. And then here what we're looking at in precipitation is, do we exceed the solubility product so that the solution precipitates, or do we exceed the solubility of the substance? So that's what we got to look at. That's what the final focus is here. Is if we look at the slide here, we've seen this over and over again. If Q is less than K, then the reaction will shift to the right, and more solid will dissolve. So what we're looking at is, if you let's see, let me get my pen started here again. Oops. Let's try that again. For some reason the pen's acting up a little bit. All right, so what we're looking at is, like, again, silver chloride, solid. And then that becomes silver ions aqueous plus chloride ions aqueous. Okay, so if Q is less than the equilibrium constant, this reaction will go in the forward direction. And so this solid will dissolve, and so we have an unsaturated solution and no precipitation will occur. If Q is greater than the equilibrium constant, called the solubility product constant here, then the reaction is going to go in reverse in order to get Q up to KSP, and that means more solid's going to form, so you will see a precipitate. And if Q equals KSP, then you have you do have a saturated solution. So the way I want you to think of Q equal to KSP is that you have a container, you have the solution, and in the solution you're going to have, usually, doesn't have to be, but usually you have a pile of solid here. So some of it is dissolving into solution, and then some of it's going from solution back into the solid. So that's when, so if Q equals KSP, you do have a saturated solution, but no precipitation occurs because you're at the point of solubility. So remember, in a truly saturated solution, the point of saturation, the solution is homogeneous. There is no solid. You don't see a solid. So that's what I always say when we first introduce saturation and unsaturated. You can't tell the difference between saturated and unsaturated. At the saturation point, this solution still looks like an unsaturated solution. Now, when you add some more solute, if it sinks to the bottom and you stir it up and it doesn't go away, then you know you were at a saturated point. But if you add more and then this dissolves, then you are still in an unsaturated solution. So just keep that in mind, that you can't tell the difference between saturated and unsaturated until after you add some more and see what goes on. Or mathematically, if you haven't reached the solubility of the substance, then it's unsaturated. Right at solubility limit, it's a saturated solution, and beyond it's a saturated solution. So just keep that in mind. I think that's an important point there. Now, a supersaturated, that's the one that throws students the most too. It's when you have Q greater than K, all right? And it should precipitate out, but it doesn't. So here's what it looks like. I'll show you on this next slide. I'll show you what a supersaturated, and you should look this up. Just Google YouTube videos or go to YouTube and Google examples of supersaturated solution, because I think it's really cool to watch. But here it is. This solution, if you look at it right now, it looks like an unsaturated solution, or it could be a saturated solution. We can't tell. It's all clear. It's colorless. And then they have one little crystal up here, one little crystal, and they drop the one crystal into the solution, and bam, all of this forms here. So that tells me that this is a supersaturated solution, because if it was just saturated, the one crystal would sink to the bottom. You stir it around, it doesn't look like it dissolves. But you add one little crystal and you get all of these crystals, that tells me it was a supersaturated solution. So usually what happens when Q is greater than KSP, as soon as you add one drop, you start to see a precipitation reaction. Or if you add multiple drops, in this case probably. But here, when you get one crystal in or one drop in and you get all of these crystals formed, that tells you that was a supersaturated solution. So what is a supersaturated? You have the conditions of Q being greater than KSP, but the solute stays dissolved in the solution, and then you need a little bit of a oomph to cause it to precipitate out. So what are the ways to oomph it? You add a seed crystal, or you can take a glass stirring rod and kind of scratch the inside surface of the glass, and it'll cause a crystal to form there, and then all of a sudden it'll precipitate out. It's kind of a neat thing. I would encourage you to look at a couple of videos on YouTube to see what that looks like. But the bottom line is, this is the theoretical part, that Q is greater than KSP. You don't have a precipitate. If you had a precipitate, then you know it would be saturated. If that's generally what happens. But if you don't have a precipitate and Q is greater than KSP, then you have a supersaturated solution. All right, so this is the problem I'm talking about. This is a very important problem. We use this in a lab a lot, and that is you have two substances. In this case, you have a lead 2 nitrate. And again, you should know that this substance is water soluble. And you go, I don't know that this substance is water soluble. Well, that means you need to go back and memorize those solubility rules. It's that important. So lead 2 nitrate is water soluble. And we're going to combine that with sodium bromide, which is also water soluble. All group 1A compounds are water soluble. And I should put an AQ, but I'm running out of room, so I'm not going to do it. All right. So when we mix these two things together, we get lead 2 bromide. And that is a solid. It precipitates out because the solubility rules say all chlorides, bromides, and iodides are water soluble except with lead, mercury, or silver. So that precipitates out, and then we have the salt, sodium nitrate. And we know that that's water soluble, so we'll put an AQ to represent that. So the question is, this concentration is 0.01550 molar. And the sodium bromide is 0.00350 molar. And the question is, will the concentration of the lead and the bromide exceed the solubility product for lead to bromide? That's what we're trying to do here. So we have two separate substances that are water soluble. They're in two separate test tubes. We pour them into the beaker, and what we want to know before we actually see this reaction is we want to be able to predict whether it will precipitate out or not. All right? So what do you think? Well, it's not as easy as just looking at it and coming up with an answer. So let me erase this so we can see other components. So let me just erase all of that. But that's the process right there. Okay, so let's move to the next part of it. So here's what you got to know. You know that sodium nitrate is soluble in water. Here's the solubility rules. This is in Chapter 8. You need to memorize that. I can't stress that enough. You've got to memorize the solubility rules. Especially, I just memorize this part, and then I assume everything else is insoluble. Now you say, what about sodium hydroxide? Well, we know, according to the rule, all sodium compounds are water soluble, so that's why we don't worry about that. So that's why they talk about exceptions over here. But just memorize the top part. It's not that hard. Get you some flashcards. Put on one side one rule and the other side the exceptions or something like that, and go through them. But you have to know that. It makes it much easier. All right, the solubility product of lead to bromide is 4.67 times 10 to the negative 6. Nope, I don't expect you to memorize that. That's given in a table or given into the problem. All right, what I do expect you to be able to do is, based on the equation that we wrote, lead to nitrate reacts with sodium. What did I do there? I didn't do that right. Yeah, reacts with sodium bromide, and then forms the solid lead to bromide. Yeah. Plus sodium nitrate, which we're not really interested in. So there's my balanced chemical equation. So we're not interested in that. That's a spectator on. So what I do expect you to know is that if we look at the solubility of lead to bromide, that is equal to, yields the lead 2 ion plus the 2 bromide ions. That you can write the solubility product for that. Expression. So KSP for that equals the lead to positive concentration times the bromide ion concentration raised to the second power. So again, that's from chapter 15, right? Take any chemical equation and write the equilibrium expression. This one's called a solubility product expression. So I do expect you to be able to do that. That should be easy. So what we know is, we know what the KSP is. KSP is here. We're going to plug that in there. We can figure out what the lead concentration is, the lead 2 ion. So up here, this is the concentration of the substance, and it's 1 to 1. So that is the concentration of the lead, 0.0150. All right. And then we know that the sodium bromide, the concentration is 0.00350. So you may be saying, well, don't we multiply that by 2? No, because we're not starting with this lead to bromide and making this. We are we have this concentration of the bromide and we have this concentration of the lead 2 positive ion. Now, we do need to square this. I'll go with that. But now what we need to find out is when we calculate this, that's going to be Q, because we don't. This is initial concentrations, not equilibrium. So if Q is less than KSP, then the reaction is going to go this direction and we don't form a precipitate. If Q is greater than KSP, then the reaction goes in reverse and we are going to form the precipitate. So that is the process in determining when we add 2 dissimilar substances, mix them together and they form a precipitate. Ultimately, what we have to do here is calculate Q, and then based on Q, we're going to say a precipitate forms or it doesn't form. All right, let's see. I'm going to click this. It may get a little messy here, but so here it is. Just like we said, this should be squared. It's not raised to the second power there. Right? There's a little typo right there. So we should get 1.84 times 10 to the negative 7. Let me just make sure that's right since there's a typo there. So we take 0.0150 and then we multiply that by 0.0035 squared. And yeah, we get that number. So we look at this value, which is Q, and Q is less than KSP. Here's our KSP up here. Since Q is less than KSP, no precipitate forms. So that's the power of this calculation, is before you added a certain concentration of lead-2 nitrate and a certain concentration of sodium bromide into the same reaction container, same beaker, you're able to predict whether you think a precipitate will form or not. So Q being less than KSP, no precipitates form. Now, if Q is greater than KSP, you can't for sure say a precipitate will form. You'll either have you can say that you either have a saturated or a supersaturated solution. Again, sometimes you add things together and Q can be larger than KSP, and if not, we just don't have that spark for it to precipitate out, and therefore you'd have a supersaturated solution. All right, so let's have you guys try that one. All right, so hit pause, try to work this one out, and see what you get for an answer, and then I'll work it out here, and then we'll see what's going on. So same thing. Same thing. Lead 2 nitrate, aqueous. I got more room here. All right, and we're going to react that with 2 moles of sodium bromide, aqueous, and that's going to form lead 2 bromide, solid, plus 2 moles of sodium nitrate. So that's my first equation. Second equation is solubility equation. Lead 2 bromide solid yields lead 2 positive ions aqueous and 2 bromide ions aqueous. And so the KSP for this, the solubility product, is equal to the lead 2 positive concentration times the bromide ion concentration raised to the second power. All right, so we know that this is 0.0600 molar. Again, 1 to 1, 1 to 1. And the bromide is this number. So it's again 1 to 1 in the sodium bromide. All right. So let's calculate that out, see what we get for an answer. So we have 0.06 times 0.0158 squared, 1.49 times 10 to the negative 5th. So this is Q. This is not KSP. Q is 1.49, or let's just say 50, times 10 to the negative 5th. All right. So then we compare that to the KSP. So let's flip back a slide. And it's 4.67 times 10 to the negative fifth. So Q is greater than K. And because Q is greater than K, this reaction is going to go this way, and the precipitate is going to form. All right. I like these problems. It's kind of neat. I mean, you're predicting something before you actually do it in the lab, and you know, that's why we do all this. It's so that we can predict things that happen experimentally, and we expect that when we do these calculations based on the concepts, we should get these answers. Now, again, could be surprising. You could add these together and you don't see a precipitate forms. You go, well, I should definitely get a precipitate. Well, you probably have a supersaturated solution then. So you go, why would I ever use this in real life? Well, the reason why you would use this is you want to separate one substance from a mixture. Like you want to separate the lead to bromide from the rest. So it's kind of like it's a purification process. Right now you've got the lead to bromide separated from the rest of the solution. You could pour that through some filter paper. The lead to bromide would stick to the filter paper. The rest of the ions and the solvent would go through the filter paper. And you could actually do successive ones of that to purify the substance. So that's one of the reasons why you want to use solubility products and solubilities to selectively precipitate what you're interested in isolating. All right, so here's a good problem. All right, so here it says the magnesium and calcium ions present in seawater are these concentrations and can be separated by selective precipitation with the potassium hydroxide. All right, so what minimum hydroxide ion concentration triggers the precipitation of the magnesium 2 positive ion? All right, so my first question to you is what precipitate are we talking about? And which one of these substances is going to have the largest KSP? All right, you could hit pause, think about it. All right, so what we're looking at is magnesium hydroxide precipitate. And we're looking at calcium hydroxide precipitate. Now, we're trying to precipitate out the magnesium. So we know that we want this to have the lowest KSP. We don't want it to form the ions. We want it to stay as the solid. So magnesium should have the lowest KSP. All right. So let's look at the problem. And I probably need to erase. All right. So we got to calculate Q for magnesium hydroxide. So magnesium hydroxide dissociates, I should say, into magnesium 2 positive ions and 2 hydroxide ions. Here's my expression. I plug in the initial concentration of the magnesium ion. Where did I get that? Right here it is. Okay. And then the hydroxide ion concentration is what I got to solve for. All right. So when Q equals KSP, the KSP for magnesium hydroxide is this. I don't know what the hydroxide ion the minimum hydroxide concentration for saturation is. That's what I need to find out. So I'm solving for the hydroxide ion, and I get 1.9 times 10 to the negative 6 molar. So to reach the saturation point, I have to add this amount of hydroxide ion to react with the magnesium ion to reach the solubility limit of magnesium hydroxide. So if I actually want to see precipitation, I have to exceed this amount. So this is the equilibrium amount. This is the equilibrium amount, but I need to exceed that amount in order for the precipitate to be formed. So what we've done here, we have precipitated out the magnesium ion from the seawater, and the calcium ion still remains in the seawater. It's neat stuff, neat stuff. Now you've separated out the magnesium. Good problem. All right, and you could do this one. Should be pretty much the same process as that. All right, this is where we're going to stop. I'm not going to cover the complex ions. I don't really think it's as important at this point. I'll talk about, let's do this. Let's do it conceptually, not mathematically. So conceptually, so let's talk about it conceptually, because it does happen in the lab, and I find students really get upset in the lab when this happens. So you're following the lab, and it says to add a certain number of drops of silver ion, like silver nitrate, in order to form a precipitate. Well, you see students in a hurry, and instead of counting the drops and being careful in how much they're adding, they just squirt a bunch of silver nitrate into the test tube. And they keep doing the reaction, and nothing happens. And so they're like, well, what's going on? Nothing is happening. Well, what you've done is you've added too much silver ion, and it's created a complex. So when you have a complex, then it may not form a solid precipitate. So normally when you add a little bit of ammonia, ammonia reacts with water, forms a hydroxide ion, and so then the silver ion would react with the hydroxide ion and form silver hydroxide, and it would precipitate out. But if you add too much ammonia, the ammonia starts to react with the silver and forms an ammonium complex, and it's aqueous, and it doesn't precipitate out. And so you're thinking something's wrong with the reagents of the experiment. It's like, no, that's not what's happened. You were supposed to add just a little ammonia to form hydroxide, to form silver hydroxide. In fact, you added too much ammonia, and now you have a silver ammonium complex. So you can kind of see that. Let's see, maybe they show us, they don't show it on this slide, so that one's not probably a good example, but there's the ammonium complex.